Спасибо. Так. Начинайте. Professor?
Yes?
Would you please also turn on your camera?
Well, it is on, but how do I show my...
That's it. I can see your face now. Like,
Yeah.
it just disappeared for a minute.
It is on, actually.
We are live, actually. Так, здравствуйте. Сегодня мы продолжаем серию наших гостевых лекций в рамках проекта «Умный четверг». Сегодня у нас в гостях профессор Назарбаев университета, департамента механической и аэрокосмической инженерии, профессор Desmond Adair. Hello, today we are continuing our series of guest lectures, and today our guest is Professor Desmond Adair. He's a professor at Nazarbayev University of Mechanical and Aerospace Engineering Design Department. Also, his research interests include computational fluid dynamics, aeromechanics, and structural vibrations, among others. Professor, I think you may start.
Okay, Alina. Well, thank you very much for this invitation to give a small talk. It's a great privilege, I think. And I am a professor at Mechanical and Aerospace Engineering, and I come from the UK. I have a PhD from Imperial College, and most of my life I've worked in the aerospace industry. But this last 10 years or so, I've been at Nazarbayev University. And one of the topics I am interested currently in is hydrogen, especially fuel cell technologies, and also from a mechanical engineering point of view, hydrogen transportation, how actually we can do that. Within this university, we have a very strong research group looking at battery electrical vehicles, which in my opinion, maybe not theirs, is suitable for ordinary saloon family type vehicles, vans maybe as well. But if we want long range trucks that can carry a lot of material, if we want long-range trains, if we want aircraft that can fly for a very long time, or ships to transport things, in my opinion, we need to resort to hydrogen. That is my opinion, not the opinion of some people. Okay. Now, what is hydrogen? Hydrogen is the lightest, simplest, and most abundant chemical element in the universe. It occurs mostly, it doesn't occur by itself, which is a good job because it's very explosive, but it does occur in water, and as you know, we've got plenty of water, and natural gas, and at the moment we've got plenty of natural gas, and its molecular form is H2. Now, how do we produce hydrogen? How do we get it into a form that we can use it? You know probably from your school days, which you're now experiencing, that electrolysis will produce hydrogen, and it can be then separated and stored in pressure tanks. However, it's been found that reforming, as it's called, some of the natural gases or even petroleum can separate out the hydrogen within the organic compounds. And that to me is the way that it's going. Now, unfortunately, that is not a zero emission process, but it is a lot less than using petroleum or diesel. So I would just point out that there is a little fault there in that hydrogen can only be produced in substantial quantities where there is a non-zero emission process. So there is some carbon monoxide, there is some carbon dioxide coming from that. Why should we use hydrogen? Well, in many ways, hydrogen is the perfect fuel. In combination with renewable electricity, it can be produced, stored and used to generate heat and electricity without, within that process, any greenhouse gases or air pollution. So as soon as we have pure hydrogen, then we don't need to worry about emissions anymore. All we get coming out of the tailpipe of a vehicle is water, either in vapor form or usually it has condensed by the time it gets to the end of the tailpipe. So why isn't it usually used? Well, people have used it in the 1930s and so on to terrible effects, in that they found it was very explosive. And in some countries it has been used for domestic heating and cooking, but again it's explosive, so people are afraid of it actually. Production of town gas, mainly from coal, which was a dirty process, could result in hydrogen, old coking coal as it was called. Historically, petroleum products have been used as transport fuel because of their wide availability. So in other words, it was easy to use petroleum and diesel, and there was plenty of it. And nobody in those days was really worried about what was happening to the atmosphere. So that's why petroleum and diesel won out and hydrogen was left behind. Is hydrogen dangerous? Yes, it is. It's highly flammable and it can form explosive mixtures with air. In many ways, hydrogen is safer than petrol and diesel. I say that, but some people wouldn't. The chance of forming explosive mixtures is limited in that hydrogen is 14 times lighter than air. So if you have a spill or an escape, then the hydrogen goes into the atmosphere and it climbs high up in the atmosphere compared to petroleum and diesel. And therefore, yes, it explodes, but it explodes well above your head and doesn't affect you. Hydrogen in vehicles is stored at high pressure, usually about 350 atmospheres or 700 atmospheres. So it becomes liquid actually when it's being stored. Now the fuel cell, which would be part of the hydrogen experience, we have a fuel cell which works through chemical reaction. But in this, it's not like petroleum or diesel. It has no combustion. There's simply a chemical conversion of hydrogen and oxygen into water. And within that, then you get a amount of energy which you can then harness to produce electricity. And the reactions that produce electricity happen at the electrodes, the cathode and the anode, which I'm sure you're all very familiar. The positive one called the anode and the negative one called the cathode. And in between they are separated by some electrolyte barrier. Now, it doesn't happen to be, have to be a liquid barrier. It can be some sort of gel, or it can be even solid. And actually people are beginning to prefer solid barriers. The point of the barrier is that it only allows H+ to go across it. It does not allow the electrons to go across it. The electrons have to go the long way round through the circuit, and those electrons then produce the electricity which drives the motor, which drives the wheels of your car. So that's the point of the electrode. Now, of course, one fuel cell wouldn't produce much, maybe about 2.8 volts or so, which isn't a lot. And therefore you have to build these things up in what's known as a fuel stack. And if you look at the bottom left-hand corner, you'll see how it's all arranged with anodes, PEM, and cathodes and so on. And then you have what's known as plates which collect the electricity. And there's a picture of a typical fuel cell on the right-hand side. The main problem compared to batteries with fuel cells is, first of all, their cost. They are quite expensive. Now, this might be because of mass production. The battery electrical vehicle is well on compared to the fuel cell electrical vehicle, and therefore the mass production or semi-mass production going on at the moment brings the cost down of, say, the battery electric vehicles. However, there is built into fuel cells a lot of circuits, and this will increase the cost no matter what you do. The equivalent materials that you need are not that much more expensive than batteries, maybe the same. But you do have 4 subsystems that must work perfectly together. You have a hydrogen tank. If you look carefully at that diagram, you have a hydrogen tank, and the hydrogen goes along the blue until it reaches the, this makes it go on, along the blue until it reaches the fuel cell. And then you also then don't waste hydrogen. You bring it back into the system using a pump at the top. At the middle bit, you have, if I can find it, sorry, the bottom bit is where the air comes in, I think. Sorry, the compressors where the air comes in, which is the sort of green bit, and that brings in the air, and then you get the hydrogen and the air reacting within the fuel cell. Now you also have, so you have a hydrogen circuit, which has a whole lot of little gadgets in it to control the hydrogen, because hydrogen has to come from very high pressure to a reasonable pressure that the fuel cell can withstand. You have an air circuit, and you have a cooling circuit, which is the same as any car, really. However, the most important one, in my opinion, is the humidifier circuit. Unless the humidity at the anode and the cathode are at a certain level, quite high, maybe 60 to 80%, then the fuel cell doesn't work at all, or it doesn't work very well. So keeping the air humidified, in the old days they just kept the air humidified. They thought that would be good enough. But nowadays, both the hydrogen gas and the air coming in are subject to humidifiers. And humidifiers are just sprays, just like if you were spraying something over your face to avoid mosquitoes or something. And they spray water, and then that humidifies the hydrogen gas and the air. And when that's correct, and that must be kept correct, then you get the fuel cell working at the optimum. What's the benefit of fuel cells? Well, they're versatile. You can build them from any scale, milliwatts to megawatts. So they can be used for very low power, even for just, you know, recharging your phone or something. But I think that would be a bit of a waste. I think we have other ways of doing that far cheaper. 2 megawatts of power, so they could be used for heating complete buildings and providing the electricity for complete buildings, for example, which would be a better use for them. Also then buses would be, in this city, for example, buses or trains would definitely, it would be more efficient to use fuel cells. Now, the environmental performance, hydrogen cells don't produce air pollutants or greenhouse gases. However, as I've said, to actually get the raw hydrogen, you do have to actually produce some air pollution, but it's greatly reduced. Energy efficiency, well, if you know anything about IC engines and diesel engines, they themselves may be 50%. Diesels maybe nowadays 60%. Until you go through the gears and all the rest of it, then you might get at the wheel, the drive wheel, maybe 30%. But these fuel cells can be up to 90%. It's well known that if you have electricity compared to mechanical movement, then you get a much quicker response for a start, and your efficiency does go up. So fuel flexibility, well, you can keep going on the methanol and ethanol, but if they run out, you have biogas, which is very common in South America, for example. It depends on the climate, but biogas is very common, so you could use that. And you can also use petroleum oil, sort of oil and petroleum to get the hydrogen from it, which may be an option. I'm not sure of the actual economics of that. It mightn't be great. Complementary fuel cells are readily to be combined with such things as batteries, of course, wind turbines, solar panels, supercapacitors, etc. But then so are other energy technologies, because I mean, hybrid cars at the moment are IC engines and batteries, for example. So that's not a big plus, but it has to be said that they can be combined. Applications, many fuel cell products are available today and are becoming a commercial option. Now, mainly you'll find that they're not out in the general public. If you have a big company like, say, Amazon, who has a big warehouse, then they could have fuel cell trucks, but because in that warehouse they have the means of putting in extra fuel without going down the road and trying to get fuel from the local petrol station. It's the same with buses and vans and, say, refuge trucks for the local council or the local city council. All those things are very good for fuel cells at the moment, because all those companies can have in-house ways of refueling the infrastructure. The infrastructure is not out with the public at the moment, and that would need to be developed. Another near-term application is combined heat and power, which one of you listening used to hear me going on about in thermodynamics, where you can actually produce a system where you have the heat and the power complementary, and you can then get a good electricity and heat basis for even a small town or a small village or just one building. Larger HGVs, trains and ships are also being developed. Now, trains, especially this last month or two, are on the go in some countries and are being tested. And maybe next month, within the United States and the UK, there is a an airplane, an aircraft that's being developed as well. Ships would be very, very good, providing we can prove that fuel cells are very reliable. Because if they're not, you don't want to be in the middle of the Indian Ocean without an engine. Now, fuel cell vehicles, so there's some of the ones that I was talking about. The lower one on the left is a refuse truck, vans, buses, and actually, amazingly so, forklift trucks are way ahead. And also on the right-hand side, then you have a picture of the layout of a typical fuel cell car. So it's a little bit different. The tanks are very, very much double insulated because it's hydrogen. And you have electric motors. You do not have IC motors, so it's very quiet, very much like battery. So, and this is the combined heat and power fuel cells, which are small scale or large scale. And in Japan, they have some of these small scales, and in the US, they're looking for a combined way of giving heat and power out, because if you don't combine the heat and the power, then you lose the heat, and that's very inefficient. So you have to have some way of bringing the heat back into the energy producing process, which is the fuel processor on that diagram, and adding then to the actual way of producing energy. Otherwise, it's very, very inefficient, maybe 40% or something. And nowadays, in the old days, when I was young, nobody ever thought twice about that. They used to just watch it going up the chimney. But nowadays, engineers are very, very acutely aware that they must recycle energy. So I produced this for comment, and any of you are absolutely allowed to comment on it. In 3 years, where will we be within Kazakhstan regarding fuel? Now, the green is available and viable financially without subsidy. So I say that if Kazakhstan get a move on and take the right policies, you could have buses, forklift, and delivery vans after 3 years. And if they then decide, well, we'll put a bit of money into this, they could have also passenger cars. Now, there's a very small company in Almaty looking at that at the moment. And they could have residential CHPs, which I think would be a very, very good thing in this country, and specialized trucks. But I don't think for the foreseeable, after 3 years, that they would have HGVs and trains. I don't see, first of all, the market for it, or even the need, the push for it to give the authorities a push so that they will have it, because they have decent enough trains and they have plenty of fuel around this place. After 5 years, all those would go green, in my opinion, if the right policies are taken on board, and then they could be thinking about trains and HGVs at that stage. And so that's just the same there. The near term, over the next 50 years or so, we may have a transition. We will have to have a transition to a more sustainable situation. And in my opinion, hydrogen is one of those. But as you see on the diagram, you can incorporate solar, wind, natural gas, biomass. I'm not sure about that in this country with the weather, but maybe it can be imported, etc., etc. Now, the infrastructure, this is one of the big things that's holding everything back regarding these new technology transportation methods. And it is an important consideration. How do you do it? Do you have compressed tube trailers? You know, something akin to the way they transport petroleum. Do they have highly cooled liquid trucks? Well, could be a possibility in this weather. And compressed gas pipelines. I doubt the last one, really. That would be too open to a lot of trouble, actually. Not least people could do damage to them if they were so inclined. But there is a combination of that could be used, which I've laid out there. Now, time is going on, I think, so I'll have to hurry up. There's a picture of the tubes that you see up at the top. And also then I mentioned again about the preferred way, which could be pipes. I'm not sure about that. Or another way is to actually manufacture the hydrogen on board. You could have a special machine, which is not too light, it's a bit heavy, and reform, say, methane and produce the hydrogen on board. So all you would be doing is refueling the methane. There's pipes. Well, they're okay. They've been going for 50 years or more with oil and so on. But hydrogen, to me, is a different kettle of fish. I'm not sure that people would be prepared to put too much investment into that. Liquid hydrogen, the cost due to electricity need for liquefaction, 30 to 60% of the total liquefaction cost, and may represent a significant CO2 footprint. So there's a bit of a disadvantage there. So what I'm saying is that this infrastructure, how we do this, is by far not decided. That is the end. I hope that was okay. So this talk is for open discussion, because some of these are my views, and if I can get my picture up now, Alina, as you asked for. I don't know how to.
You need to stop sharing your screen. That's it.
How's that? Okay.
Yeah, we can see your face now.
All right.
Well, I guess transitioning to this hydrogen like infrastructure and stuff in Kazakhstan will be a bit hard thing, because people are still cautious about the outcomes of hydrogen, and even the word hydrogen, considering the history of Kazakhstan and Soviet Union. And it's like a very hot topic now. Not like in discussion, even if it, for example, wind energy is accepted pretty well, but thinking about hydrogen energy, it's only people who research this stuff, they're more open to start using cars like on hydrogen, on fuel cells, and like it's more about knowing stuff and more spreading it into the masses, I guess. Maybe you can share you can share what research are you doing now with like students in Kazakhstan, or is your research is not attached to a place specifically, but like only about models?
My personally research this last year or so for fuel cells, well, first of all, for a PEM, which is a proton exchange membrane fuel cell, we have developed a model for the energy paths through the fuel cell, a simulation model. And also, I'm not sure if I should use this word with you, Alina, an exergy path. So energy and exergy simulation, where the exergy is looking at the economics of the fuel cell and the quality of the energy as opposed to just the energy, which is part of thermodynamics. So we have quite an extensive simulation package to look at. We based it on PEM, which is a type of fuel cell, which is one of the types that they use in small aircraft, for example. But it can be extended to other fuel cell types, solid oxide or something like that. So that's one thing. Now the second thing is that when you have a high pressured container of hydrogen and you open the valve, the hydrogen comes out at a tremendous speed. And in fact, it can go supersonic. And therefore, we're looking at the shock waves down the pipe just after the opening of the pressure vessel and seeing how those shock waves develop, because we have supersonic velocities. So that's another thing that we're modeling using CFD, using ANSYS, actually. So those are the two main things that in this last, say, 6 months, maybe, we've looked at.
Okay, thank you. I guess our students will be, there are students that are interested in hydrogen technologies, and they are asking which year, like at the university, they should approach professors and start doing research, especially like 12th graders. About, they need a strong base first, right? And after the second year, maybe, right?
At undergraduate level?
Yes, at undergraduate level. What can they do at that level?
Well, as you know yourself, you have to go through thermodynamics. I mean, you can't get to grips with any of this unless you go through thermodynamics. And then you have to find some university that also does the thermodynamics of fuel cells. Now, there's not too many of those about. There is one here, it's called Nazarbayev University. But you'll find in most thermodynamics courses at undergraduate level that they restrict themselves to the usual refrigeration, IC engines, Rankine, and that other guy whose name I forget. Those traditional types of things. But you have to, if you want it at undergraduate level, there's not too many around. But at master's level, yes, you then can find quite a lot in Europe, in Germany especially, where they specialize in the new energy technologies. And one of the subsections that they would cover would be fuel cells and the thermodynamics of fuel cells as well. But they will also, of course, cover wind, and they will cover batteries and probably solar as well. The trouble is nowadays that it's not purely a mechanical thing. Things are getting mixed up, but mechanical engineers are used to that. They were always mixed up. In that it's cross, there's a bit of chemistry, there's a bit of electricity, quite a bit of electricity, and there's a bit of mechanical. But people like me have always been used to that. We've always had to take the electricity bits and the chemical bits that we need, and then work with them within the mechanical area. Inside batteries, for example, you might think there's nothing mechanical inside batteries. It's all chemical, electrochemical, just electricity coming out of it. Where's the mechanical engineering? There is a lot of mechanical engineering within batteries because of the heat factor and because of the chemical factors which cause stress and strains in the anodes and the cathodes, and sometimes even in the join between the electrolyte, if it's solid, and the cathodes and anodes. And it's those stresses and strains that people have suddenly become aware of that causes the internal resistance of the battery and therefore makes its efficiency much, much less. So if we can model or do experiments that actually reduce the stresses and strains and show that if we change the material, if we change the geometry in some way and the stresses and strains go away a bit, then you've got a much better battery. So mechanical engineering is very far-reaching, actually. Just a little plug, Alina.
Reaching everywhere, though. Yeah, you mentioned like electrolysis and electrolytes, and we stand graders. We only covered these topics this term, started covering it, and like electricity in different mediums. And they only start like this introduction to this type of thing in physics. That's why I guess.
But you will find at universities, I mean.
Sorry, Mike. There are troubles.
Yeah.
Okay.
You will find at good universities that courses, they don't start by assuming that you know too much. They start with a very quick revision all the time. And then if people are not at all familiar, you would get help to do extra reading or extra exercises or something like that. We find that actually with the master's courses here, because we take master's students from everywhere, we don't give them any introduction through much like CPS or whatever. And therefore we have to give them quick introductions and quick reading materials to bring them up to speed. For instance, with MATLAB, you're very familiar with MATLAB. But there are people that come here to do their masters and they've never seen MATLAB, for example. So, for instance, I teach a course, numerical techniques, and the first 2 lectures are all about MATLAB and bringing them up to speed. So no student should fear that they will go in and not know, I've never done this before, that type of attitude, because any decent lecturer will always try and make it as self-contained as possible, but bring it forward in a controlled way so that they're meeting new things. It would be very unfair to a student otherwise.
Yes, transitioning to university courses were kind of hard for me back then. Because of this attitude, I feared that after school I knew nothing and I will not be able to start my university life now.
But I guess, you knew maths. Every Kazakh that comes to us is very good at maths. So for engineering, there's no problem. The problem is when you're not good at maths, which happens in the UK a lot, and then you really struggle. But I've never met a Kazakh yet who's not good at maths in comparison to other countries. So I'm not trying to ingratiate myself, but I know that for a fact because I've taught them for 10 years, and they know their stuff.
Maybe Soviet system still works for that. And yeah, and NIS students, they're taking calculus in high school, and like mathematical analysis, some basics of it. And we start.
What about linear programming, linear
algebra,
matrices?
yes, we cover matrices. We cover matrices.
When I first came to Kazakhstan, they didn't do matrices. It was an awful shock to me because I remember teaching them and the calculus went just like that, no problem. And then the next topic was matrices and determinants and all. Nobody knew a thing. But now they do. Now they do.
Like back in school, we covered it, and now students are also covering it. I guess in 11th or 12th grade, the program changed. So
yes.
I guess there are additional lessons for students now. That's why they're not that active now. But thank you for your lecture. And
you're welcome.
For your, like, insights.
I hope it was okay. Okay.
Thank you. I guess. Yes, I guess we can finish our lecture. Thank you for accepting my invitation to the event.
Right. Thank you. Bye-bye.
Thank you.
Right.